Welcome to the third lecture in Module 6 on finite volume method. In the previous lectures we had considered the basic introduction to finite volume, best approximation of finite volume integrals and interpolation schemes. In this lecture we would focus on application of finite volume method to scalar transport problems. So let us have a recap of the second lecture which we had earlier. So we discussed interpolation methods. In particular we had a look at upwind interpolation, linear interpolation and quadratic upwind interpolation method. We also briefly mentioned few other interpolation methods. Now in this lecture we are going to focus on application of what we learned about finite volume formulation to scalar transport problem, and as a model example we would take one dimensional steady state heat conduction problem. So outline, we will first have a brief look at the implementation of boundary conditions, and we will just review the characteristics of finite volume algebraic system on an structured grid, and then we will have a detailed look at the derivation and application of the method to 1D heat conduction problem. So we will have a look at problem statement, finite volume grids which we can use for this problem. We will discuss the discretization using finite volume method and how do we implement boundary condition with different grid choices. And then we will have a brief look at solution of algebraic system and computer implementation aspects. Now let us have a look at how do we implement boundary conditions in finite volume method. The things are fairly similar to the way we did in finite differences. Now in case of finite volume, for each control volume we get one algebraic equation, and the volume integrals are computed for each control volume, whether that is in the interior or close to the boundary, in exactly the same way. The boundary conditions affect only the computations of boundary fluxes for the CV phases which coincide with the domain boundaries, and these require special treatment depending on the prescribed boundary condition. And these boundary fluxes must either be known as a specified flux boundary condition, or they can be expressed as a combination of interior values and boundary data. And if we have a boundary condition which involves gradient of a variable, we can use one-sided difference formula in exactly the same manner as we did in our finite difference method. Now a brief look at the algebraic system which we would get when we apply finite volume discretization. So discretization using finite volume yields an algebraic equation for each control volume in terms of the variable values at its computational node, which would most likely be at the centroid of this control volume and its neighboring nodes. And this equation would be a linear equation if a problem is linear, or it would be a non-linear discrete equation if it is a non-linear problem. Now let us have a look at the way we can represent it. Even for a non-linear problem we can represent it as a quasi-linear equation, and this quasi-linear equation for a generic scalar quantity phi for a generic control volume can be represented as a capital P into phi capital P plus summation over L, A L phi L is equal to QP. Now here this index P that represents the computational node which is linked to the CV, that is which represents the centroid of the control volume, and L represents the neighboring computational nodes which are involved. Now how many number of computational nodes would be involved? That would depend on the choice of interpolation schemes and the choices for which we have used for the evaluation of surface and volume integrals. In QP we would have dumped all the terms which pertain to what we call the load vector, which might come from the sources or from the known boundary conditions. Now this is an equation which we would get for all the control volumes. This equation would be modified for the control volumes which are close to the boundary, and if we look at all these ones, now please note that these coefficient AP and AL, they are functions of the grid size, that what is size of finite volume, and the metal properties. Now in similar to the way we had called as P and its neighboring nodes, that they form a computational molecule, if we have used a structured grid in finite volume analysis, the same terminology is also used in finite volume context, and with these structured grids we would use compass notation. We have already seen it in the first lecture on this module, that how do we represent various nodes and faces on an structured grid in finite volume context. Now, if we collect all the equations, all discrete algebraic equations for all control volumes after incorporating the effective boundary conditions, we would get a system of algebraic equations form capital A times capital phi is equal to Q, where capital A would be our coefficient matrix or system matrix, phi is a vector of unknown nodal values of phi at the computational nodes, and Q is a known vector. Now, this vector A, once again, if you look back our the equation for one particular control volume, we saw there contribution coming from only few nodes, which are the neighbor nodes of the computational node. So, this matrix A is always sparse. In fact, its sparsity pattern is fairly similar to that obtained in finite difference method if we have used a structured grid, and would be fairly similar, it will be a banded structure if we have used an unstructured grid finite volume formulation. Now, let us come to our example problem, which we will discuss in detail, that how do we apply finite volume application method to solve a particular problem. So, as a template, let us say we take one dimensional heat conduction problem. For the sake of simplicity, we are going to restrict ourselves to steady state problem. As far as the basic discretization technique is concerned, it would be exactly the same even for a time dependent problem. The only difference would be, in the case of time dependent problems, our discrete finite volume system would be a system of ODEs in time, which we can solve using the time marching schemes, which we had discussed in the previous module. Okay, and let us assume that we have got a slab of width L with thermal conductivity K and the heat generation Qg. If you are looking at the integral form for energy equation, that is how it looks like. Integral over the surface K gradient of T dot dA plus Qg d omega, this is the volume integral, which gives us the effect of the heat generation in the volume is equal to 0, or if this is a partial differential equation, which you will get K del to T by del x square plus Qg is equal to 0, wherein we have assumed K to be constant. And to obtain a unique solution to this problem, we have to apply the constants in the form of boundary conditions. So, constants could be in the form of Dirichlet boundary condition of what we call a specified temperature at the boundary, T is equal to T bar. We can have at some part of the boundary what we call Neumann boundary condition or a specified flux, Q is equal to Q bar, or we can have convective boundary condition specified at the boundary, Q at the boundary given in terms of the convective heat transfer coefficient H into T minus Ta. Now, let us have a look at what choices we can make for discretization and how do we proceed with finite volume formulation to solve this problem. So, let us have a look at our board, this finite volume analysis of 1D heat conduction. So, this was our slab. And we will have some boundary conditions specified at both ends. For the time being, let us not put any constraints. Okay. Now, we have got two choices for the finite volume grids. Choice 1, choose the computational nodes. and at ends end points of the domain we will have computational nodes. This is very similar to the choice which we had made with our standard finite difference formulation, that this was our domain. Depending on the number of divisions we will have, we have chosen our computational nodes. And our control volumes would be taken to be these mid surfaces okay. So, these are control volume faces. Okay. So, for instance, this becomes one control volume, similarly this one would become another control volume, and so on. So, this is one choice, and remember here at both ends, let us call these ends as x is equal to x a and x is equal to, or rather x is equal to 0 and x is equal to L. So, this was, we have got one node at x is equal to 0, let us call this as node as 1, 2 and so on. This is ith node P, and this is the last node. So, if you got n divisions, the last node would be numbered as n plus 1, which corresponds to x is equal to L. So, this is one particular grid, what we call, this is our face centered grid. We can make A10 the choice. Cell centered grid. Now, remember, as we discussed earlier, the cell centered grid is used more commonly in finite volume analysis. So, here we have got the domain. We will first divide it into cells. First, let us form our control volumes, and the center of each control volume, that becomes our computational node. So, we first chose our CVs, and then, so this hatched portion was our CV, and these are our computational nodes. Now, let us, if you look at two things clearly, as far as the basic discretization procedure is concerned, or basic finite volume formulation is concerned, that would remain the same. We will take a particular control volume and we would apply our governing integral equations to obtain a discrete equation for that control volume. So, whether we take a face centered grid or a cell centered grid, in both the cases the basic formulation would remain the same. The only difference would be how do we treat the boundary conditions. The treatment of the boundary conditions would be slightly different in the face centered grid compared to the face centered grid. For instance, if we had Dirichlet boundary conditions specified both the ends of the slab, in this face centered grid where the vertices are coincident with the boundary ends, we get a very simple equation T1 is equal to Ta, that becomes our discrete equation at, let us say, the node 1, and similarly Tn plus 1 is equal to Tb. Okay. And for imposing the flux boundary condition, we will have to choose a slightly different computational volume close to the boundary. These aspects we are going to discuss next. But first let us have a look at the finite volume formulation for a typical control volume. So, we will choose a discretization with a uniform grid, okay, and we will implement our boundary condition. This implementation would depend on the choice of the grid, and as we will say that for cell centered grid implementation is very similar to that discussed earlier with cell centered finite difference approach. So, now let us get our finite volume discrete equations for a generic computational node or generic finite volume. So, let us take a generic finite volume, east face and its west face, the centroid, or let us say this is the computational node, let us call it P. If you have taken uniform grid with either option, face centered option or cell centered option, the computational node would be at the center of the finite volume. Let us also draw by dotted line, let us denote the neighboring CVs. In fact, we are more interested in the neighboring computational node. This is computational node capital W, this computational node capital E, and we would now apply our conservation law, that is in this case our integral form of the heat conduction equation to our chosen control volume. So, apply heat conduction equation to this control volume CV. The area of the faces, let us say this particular face, this area is AW, the area of the east face is AE, and in this case note that AE is equal to AW, same, and what is the volume? Volume of CV, this would be basically A times delta x, where delta x is the extent of this control volume in x direction. Okay. So, first term was a surface integral k gradient of T dot dA plus we had a volume integral to take care of Qg Now, in one dimensional case, now we have got only two control surfaces. So, this in k dot dA, that becomes very simple. So, this would become k times dt by dx at the eastern face minus k times dt by dx at the western face plus, let us use our Cv Qg d omega is equal to 0, and of course, these are area integrals multiplied by the area A. So, here what we have done is we have used our midpoint rule for surface integrals. We can use the same rule to volume integral, So, if we use the midpoint rule, for volume integral, then we will get this qg d omega Cv would be qg bar delta V, where qg bar is the value of qg at the centroid, that is at point P. So, you can also put the subscript capital P if you want to be very particular. Now, we have got these two derivatives in the diffusion term, dt by dx at E and dt by dx at W. So, let us use central difference approximation. So, central difference approximation of derivatives. So, the dt by dx at E, that is our east phase, it can be written as simply in terms of the value of temperature at eastern node E. So, that becomes T E minus value at the current computational node P, T P divided by delta x, and similarly the value of derivative at the west phase, because west phase that represents the midpoint between the computational node P and W. So, this is given by T P minus T capital W divided by delta x. Okay, so now let us substitute these approximations in equation 2. So, from equations 2 to 4, what do we get? K we have assumed to be constant, let us say K A T E minus T P divided by delta x minus K A T P minus T W divided by delta x plus Q bar P delta V is equal to 0. Let us simplify this expression, we can divide by K A and multiply by delta x and rearrange the terms. So, we will get minus T W plus 2 T P minus T E is equal to Q P bar delta x square y k. So, this is the discrete equation for our chosen interior control volume. So, discrete equation for this chosen control volume. So, let us call this final equation as our equation 5. This equation has to be modified a bit. Let us say first let us account for one particular case where our source term is temperature dependent. So, suppose that heat generation term is linearly dependent on temperature. That is, we can write this as Qg is equal to Qc plus alpha times T, where alpha is appropriate proportionality constant. So, now in this case our average value, this Qp bar, would be nothing but Qc plus alpha times Tp. Okay. So, we can substitute it now in equation 5. Let us call this equation as 6. So, from 5 and 6, if you substitute it there and then collect the Tp terms, bring it on the left hand side, we get minus Tw plus within brackets 2 minus alpha delta x square divided by k times Tp minus Te is equal to q say delta x square by k. So, this is the final form, a final discrete equation for a finite volume. And now, this equation has to be modified by accounting for the boundary conditions for boundary nodes. Okay. So, that would be the only difference, and that the implementation would depend on the choice of our finite volume grid. So, this is our implementation of boundary conditions. Boundary conditions, and we will consider the two cases separately. The first one was this face centered grid, wherein this computational nodes were on the boundaries, that is, this was our domain and domain boundary 0 and L. So, the first computational node was on the boundary. Similarly, if you had n divisions, so the last computational node, that which was numbered as 1 n plus 1, is also on the boundary. Now, how would we implement different types of boundary conditions? So, let us take the case of Dirichlet BC. That is, temperature is specified. So, if T at x1 is given as Ta, then what happens for different equations for finite volumes? There is one control volume which is linked to this boundary node 1. For that, we have got a very simple equation. So, then for Cv linked to node 1. So, this was our Cv linked to node 1. We have got a very simple expression, that is T1 is equal to Ta. Let us call this equation as 8 in continuation. Similarly, if we had a boundary condition specified at the last end or the right end, which was our node number n plus 1, and this node number n, and this was our Cv boundary. So, if Cv or finite volume linked to the node n plus 1, that would have a very simple form. Similarly, if temperature is specified at right end, then discrete equation for last Cv becomes T n plus 1 is equal to T b. Suppose you have a specified temperature here is T L is equal to T b. Okay. So, in this scenario these are the equations which ought to be put in for the control volumes, and note down that these control volumes are of half width delta x by 2. So, for these control volumes which are adjacent to a boundary computational nodes, in the case of Dirichlet BC we have got very simple expression, and these two equations can be put together with the discrete equation for other control volumes to obtain our final system and solve it. Now, instead of temperature specified, suppose flux was specified. So, if Neumann BC that is this flux BC is specified, then how do we incorporate it? In that case the treatment would be slightly different. So, now let us have a look at our, suppose we are dealing with the left end, that is x is equal to 0, and here the value of the flux is specified, q at x is equal to 0, suppose let us call it as q a, it is given. So, we got this computational node 1, computational node 2 and so on, and now this becomes our CV phase, and this is the half width control volume which is linked to computational node 1. So, this is our CV 1 and its width is delta x by 2. So, now we have to write ab initio the equations, or we would apply our integral equation to this half width CV, and we would note down that the flux is given, that is this q a is equal to minus k dt by dn at x is equal to 0. If we take care of the directions, so this becomes our k times dt by dx for the west face. Thus, our boundary now coincides with the west face, the east face of a CV. So, this is given as q a. So, the equation for, so governing equation applied to CV linked to node 1 becomes k times dt by dx at face E minus k times dt by dx at face W. Of course, we will have to multiply that areas, plus q bar, where now this q bar is the average value or the value at the centroid of this control volume into delta V prime is equal to 0. And we have to be careful that what is delta V prime now. This delta V prime would be a times delta x by 2. So, please be careful about this, and in the place of k dt by dx w we would substitute our q a. So, our equation simply becomes k a. Now, dt by dx, let's use the central difference scheme in terms of the values at node 1 and the computational node 2. So, we get T2 minus T1, and please beware, this is a half width control volumes. So, this is delta x by 2 minus q a plus q bar a delta x by 2 is equal to 0. So, let us simplify this expression further. So, we get minus T1 plus T2 minus QA delta x by 2 times k plus q bar delta x by 2 whole square divided by k is equal to 0, or on further rearrangement we can write it as T1 minus T2 is equal to q bar delta x square divided by 4k minus qa delta x divided by 2k. So, now this is the discrete equation for the first control volume. So, discrete equation for CV1 near left boundary. You can apply exactly the same process or same procedure to implement if the flux boundary condition were specified at the right end. So, I would leave that as an exercise to you. So, implementation of boundary conditions. Remember, we are dealing with this first case of face centered finite volume grids, and we had this Neumann boundary conditions. So, your exercise is derive the discrete equation, discrete finite volume equation for the CV at right end of the domain if Neumann BC is specified. Convective boundary condition in this case can be handled in the similar fashion. So, that I would leave it with just a comment there, that convective flux boundary condition, convective flux boundary condition can be handled in the same manner by taking or by considering half width CVs linked to the boundary nodes. And I would leave it as 8th exercise for you, that derive the appropriate equations discrete equations if convective BCs are specified at ends of the slab. Next, handling of the cell-centered finite volumes is bit different from what we had seen with the vertex-centered or face-centered finite volume grids. So, implementation of BCs for cell centered grids. In fact, this concept we have already seen earlier when we dealt with the cell centered finite difference formulations. I would just repeat the basic approach which we use for implementation of boundary conditions in this case. This is what will happen. These will first divide our problem domain in the control volumes, and their centroids now they become our computational nodes. This is our cell centered grid. Now, if boundary conditions are specified at the ends of the domain, how do we account for these? Now, there is no computational node, there is no control volume exclusively linked to the points on the boundary. In fact, we have two boundary CVs. This is our left boundary CV or CV on left boundary, and similarly this, let us say this one becomes our CV on right boundary. So, in this case what we will do is we will introduce the concept of a ghost cell. Okay, now these ghost cells can be taken on either side depending on which boundary control volume we had taken. So, that is what we had discussed. Suppose we take the CV towards the left end. So, this is our boundary, this is our CV, and this is our computational node P. So, we will take a ghost CV and its centroid becomes what we call, like say in this case this capital W, this becomes our ghost CV and this becomes our ghost node. And we would now apply the differencing or linear interpolation, making use of the values at these ghost points. So, this is what we had done earlier in cell centered finite difference implementation. So, this is just a revision of what we have done earlier. So, suppose we had Dirichlet BC specified. Say specified at left end. So, that is what we are given is T at a small w, that is given as the boundary condition Ta. So, how do we incorporate it? Now, what we can do is we can make use of the concept of linear interpolation or averaging, and we can say this now T at the west face, this is the west face of this control volume, Tw is an average of Tp plus T capital W. So, take the values divide by 2. So, we get their average. Now, this is what becomes equal to our TA, and now use this from here we can get an expression for T capital W, that is the value of the temperature at the host node. This becomes 2 times TA minus Tp, okay, and substitute this value of T capital W in equation 7, which we have derived for an interior node, or rather we have derived for a generic CV, to obtain the modified equation for control volume 1. We can adopt exactly the same process for the rightmost CV if the temperature were specified. So, this was the first case. If flux were specified, flux BC, then of course, we do not have to do anything, we just go back to the beginning and Q at the phase W, that is already known, substitute that value in the application of the governing equations for this particular control volume, and we will get the modified equation for the boundary control volume. So, the flux BC is straightforward. So, substitute this value, the specified flux value in the integral equation. So, it is exactly the same which the way we had handled it for our phase central grid. So, exactly the same process, nothing to worry about. If we had the convective BCs, so convective flux is specified, okay. Once again the process remains similar to what we had done with the flux BC. Go back to our integral equation, substitute that value, and there would be a small catch which we will get there. We have the value at the end point of the domain, that is what is involved, that phase temperature would be involved, and now the phase temperature can be obtained using the straight line averaging procedure which we had used for our Dirichlet boundary condition. So, I would leave these expressions as an exercise for you. So, obtain the discretized equations for boundary CV for a Neumann and B convective BCs. I would just again like to remind you that these expressions will be fairly similar in the form to what we had already derived earlier in detail when we were dealing with self-centered finite difference formulation. So, that is the reason why I have given this as exercise to you. So, now we are done with the derivations of our or implementation of boundary conditions, okay. And once we are done with, collect all the equations. In this case, you can easily observe that each equation contained the values of 2 neighboring computational nodes. So, we will get what we call a tri-diagonal system. We have already learnt TDM algorithm, we have also seen the program based on it. So, you can easily use that routine to solve it. Now, as far as computer implementation is concerned, is almost identical to what we had done in the case of finite differences. So, structured grid finite volume or structured grid finite difference, in both the cases the implementation of the computer program remains almost identical. So, we are not going to have a detailed look at it, because you have already seen a detailed design of the code. Okay. So, please note this similarity, and based on this I would like to give you assignments that we have already discussed in detail. How do we design a finite difference code? A structured grid finite volume code is very similar. So, modify that code wherever the modifications are required, the FD code which we discussed in module 3, and turn it into a finite volume code for 1D heat conduction problem. You are also given development of a structured finite difference code for 2D problem. So, extend that or extend your 1D finite volume code into a 2D code for solving steady heat conduction problems. In the end, let us have a look at the numerical results for a test problem which we had already solved earlier using finite differences. This was a slab of width L of is equal to 0.5 meter with heat generation. The left end we had Dirichlet boundary condition specified, that is it was maintained at T is equal to 373 Kelvin. The right end of the slab was heated by a heater with the flux given as 1 kilowatt per meter square, and the heat generation in the slab is temperature dependent. Capital Q, this is Qg basically, is equal to 1273 minus capital T watt per meter cube. Conductivity is constant. So, this same problem we have solved using our finite difference schemes earlier, and the finite volume formulation which we have just discussed, if you implement it, this is what you should get. So, numerical results with finite volume method at interior nodes. This is based on the face centered formulation wherein the nodes are the computational nodes coincide with the boundaries as well. So, we have got the values put here at these interior nodes, x is equal to 0.1, 0.2, 0.3, 0.4 and the last node 0.5, and there is temperature values in this particular column. They are the values obtained from finite volume formulation. This was the exact solution, and the errors, you can just compare these errors. You have already got the relevant slides with finite differences, you can go back and compare, and you can easily say that the results obtained with finite volume formulation are more accurate compared to finite difference formulations. And the reason was very simple. In this case, in finite volume formulation we have used second order accurate schemes everywhere, whereas in the case of finite differences there was at the boundaries for the flux term we had used a backward difference approximation which was only first order accurate. So, we will stop here with our discussions on finite volume method, and these are our references. If you want to have further detailed study of finite volume method, please refer to these books: Computational Fluid Dynamics by Chung, or book by Fersiger and Parik, and book by Versteeg and Malala-Sekera. Specifically in this introductory course, we would not be discussing finite volume formulations on unstructured grid, which are relevant to complex geometries. So, for finite volume method applied to unstructured grid, please refer to any one of these books.